Okay, so I'm going to pick up on slide 18 of the Chapter 2 PowerPoint, and we're talking about uncertainty in measurements. So uncertainty in measurements arises due to two sources of error, and it's important that we realize that when we say error, we don't mean mistakes. We mean things that are unavoidable even though we're trying to do our best. And the reason that we have uncertain measurements is due to both human errors and what we call instrument errors. So human errors are those that arise even though we're trying really hard to do the right thing, even though we've trained ourselves to use the instrument correctly. There's a limit to how well we can do it. Instrument errors are similar, but they relate to the qualities of the instrument. So there's, you can only calibrate your instrument so well, and you can only construct your instrument so well, and as a result we get errors. So in chemistry, whenever we make a measurement, we have a rule that we always record one and only one estimated digit. What I mean by this is that we always include one digit that we've kind of guessed at. That will be, we go one digit smaller than the smallest increment on the scale. So in this measuring device here, the increments on the scale are in every 100. And so we're going to record our measurement to every 10. So this would be 100, 200, 300, and then it looks like it's a little bit past the 300. I have to decide, do I want to put this as 310 or do I want to put it as exactly 300? I can't put it as 305 because that would be estimating to the ones, and I'm only going to go to the tens in my estimate. So I'm going to estimate this guy as being 310, just a little bit beyond the 300 line. So if I look at these four different rulers here, I see that they have different scales. The first one here, the increments are in the ones. So I'm going to estimate the height of this paperclip to the 0.1s. So maybe this guy is like 2.7, 2.8. Now, if I go to this one here, what I see is that the scale is in the 0.1s, right? There's 10 lines between each increment of 1. So I'm going to estimate this not to the 0.1s, but to the 0.01s. I'm going to go one digit smaller than the smallest increment on the scale. So this looks like it is 2.5 is there, 2.6 is there, 2.7, and it's a little bit beyond 2.7. So I think it might be just a little bit beyond 2.7, and I'm going to say it's 2.71. Now, when I go to this one, this is a giant paperclip, this guy, because these are 10 centimeter markings. So this is 10 centimeters, 20 centimeters, but it's not quite 30 centimeters. So because my increments are in the tens, I'm going to estimate this to 1 centimeter. So one increment smaller than the size of the scale. So maybe this is like 27 centimeters long. Okay, so again, on this fourth one here, we've got a giant scale, and the major increments here are in the tens, but the smallest increment on my scale is actually in the ones. So 1, 2, 3, 4, 5. That's where we are there. So if the smallest increment is in the ones, I'm going to estimate to the 0.1s. So this would be 20, 25, 26, 27, and then maybe just a little bit more. So I'm going to estimate this guy as 27.1. So what you see is the digit in red every time is our one estimated digit. So the first thing to keep in mind is that the last digit is a guess. It's an estimate. So it's going to be dependent on who has made the measurement, and it's going to be uncertain. So there might be a little bit of disagreement about this. So the last digit will have some uncertainty in it, depending on who has recorded it and how well they made that measurement. The other thing that's important is because we always include one estimated digit, sometimes we'll record a 0 at the end of our number to indicate that our measurement falls exactly on the scale. There's also another difficulty is when we are measuring the volumes of a liquid, it'll often have a curved surface that we call the meniscus. And what we do is we always make sure that we measure from the middle of the meniscus. So in this case, we've got a scale here. The increments are in the ones. So we've got 31, 32, and it's exactly on the line. Because it's the scale has increments in the ones, we're going to record out to the 0.1s, and you can see that the person is measuring from the center of the meniscus, not from the edge, because you would get a different result there. So the uncertainty in the last recorded digit, you can indicate this uncertainty using this plus or minus notation. So here's a number here, 15 plus or minus 1. The last digit is a guess, it's uncertain, and this is the uncertainty in it. What does this mean? It means that, you know, our answer is somewhere between 14, that's the minus 1, and maybe out to 16, that's the plus 1. This is a bit better measurement. The uncertain digit is in the 0.1 position. Here it is here, and this is 15.3 plus or minus 0.1. So that means our true value is somewhere between 15.2 and 15.4. And here we go again. In this case, we've got an even better measurement. This was made on a measuring device that had increments in the 0.1s, and we've estimated out to the 0.01s. And this is 15.34 plus or minus 0.03. So the true value for this measurement is somewhere between 15.31 and 15.37. Now we have a little rule, and that is if the uncertainty in the last recorded digit is plus or minus 1, then you can miss out the plus or minus notation and understand that that is just kind of implied. So we won't be writing 15 plus or minus 1, we'll just write 15 and understand that the uncertainty in the last digit is plus or minus 1. The same for our value of 15.3 plus or minus 0.1. We don't have to include this plus or minus notation. It's understood that it is 1, plus or minus 1 in the 3 if we omit that. However, when we go out to this guy where the uncertainty is not plus or minus 1 in the last digit, and then we have to specify it explicitly to make that clear what we mean. So, yeah, just reiterating there, this slide's kind of a little unnecessary. If we omit the plus or minus notation, it is understood that the uncertainty is plus or minus 1 in the last recorded digit. So here's a little example problem. What should the recorded uncertainty be, or plus or minus 0.1 of the unit, plus or minus 0.01 of the unit, etc., for the following measurements made with the following devices? And our rule here is that we need to go 1 unit smaller than the smallest increment on the scale. So here we have a ruler with intervals of 0.1 centimeter. So we're going to go 1 factor smaller. We're going to record until plus or minus 0.1 centimeter. If we have a measuring cylinder with intervals of 0.1 milliliter, we need to go 1 factor smaller. So the uncertainty here would be plus or minus 0.01. Now we have a device with markings every 10 fluid ounces. So our uncertainty there will be plus or minus 1 fluid ounce. Our scale in case D here has intervals every 100 grams. So we're going to have an uncertainty here of plus or minus 10 grams. So it's quite, it's a really great technique because we can look at how many digits are recorded for our measurement, and we immediately get a little bit of information about the quality of our measuring device. Okay, so we get uncertainty in measurements due to human error and instrument error. These are not mistakes, these are physical limitations of humans and our instruments. To make it clear how good our measuring device is, we always include 1 estimated digit, but only 1. The uncertainty in a measurement can be indicated using plus minus notation, but we have a little shorthand. If it's plus or minus 1 in the last digit, in the estimated digit, then you can omit that and it'll be assumed that the uncertainty is plus or minus 1 in the last digit, in the estimated digit.